Hi everyone, my name is Kuvina and welcome to Relativity Part 7. The twin paradox is the most famous paradox in all of relativity. The basic premise is that one twin stays on Earth while the other one travels to a distant star and then back again. The space twin moves at near light speed, and so due to time dilation, they age more slowly. Upon returning, they'll be younger than the Earth twin who was stationary the whole time. The problem is that relativity works both ways. In the space twin's own reference frame, they're stationary the whole time, and it's actually the Earth twin who moves at near light speed, experiences time dilation, and therefore is the younger twin upon their reunion. So one reference frame tells us the space twin is younger, but a different one tells us the Earth twin is younger. These are contradictory, forming a paradox. So which one is it? Well, believe it or not, the twin paradox is actually still controversial. Not because of the outcome. Everyone agrees that it's a space twin who is in fact younger. The controversy is instead about the reason why this is the case. Some people say the key factor in resolving the paradox is acceleration, while others say you could still get a paradox without acceleration. And then others still say that no matter how you resolve it, it still results in unresolved philosophical concerns about relativity as a whole. Now, I could elevate one explanation over all the others, but that would go against the spirit of this series. I'll reiterate, my whole point with these videos is to explain what personally worked for myself in a way that I think is accessible for everyone. Having said that, in my own personal experience, the twin paradox epiphany came not from any individual explanation, but instead upon the realization of how the different explanations relate to each other. For that reason, this video will provide 3 different versions of the twin paradox, which are fine on their own, but work best when synthesized together. The names I've chosen for these 3 versions are the acceleration version, the inertial version, and the philosophical version. I'll be covering them in that same order, but to understand any of them, you first need to know the basics of relativity. Those are covered in depth in episodes 1 to 6, so I highly recommend you watch those first, but I will give a brief recap here. The most important thing would be the list of rules. An inertial reference frame is just the perspective of an observer that isn't accelerating. And as long as you're in one, the following are true. 1. The laws of physics always remain consistent, and 2. The speed of light remains as a constant called c. These are the 2 postulates of relativity, and they lead to several effects, including time dilation and length contraction. Basically, as an observer moves faster, time passes slower for them, and their length is contracted along the direction of motion. And in that observer's own reference frame, it's everything else that undergoes these effects. They both occur by a factor known as alpha, which becomes significant as velocity approaches c. And velocity can never reach c because velocities combine according to a very specific formula. Finally, relativity of simultaneity means that the only way to guarantee 2 events are simultaneous in all reference frames is if they also happen in the same place. This means 2 events can happen in a different order depending on your reference frame. For example, 2 observers can each see each other as younger, and it doesn't cause any issues as long as there's a distance between them. Since instant communication is impossible, they don't actually see each other in real time. Instead, the only way for them to interact is by sending finite speed signals to each other. As we saw in episode 3, when you apply things like invariance of c to these signals, the results stay consistent across both reference frames, which is why it's okay for their perceptions of time to differ. The key factor here is that the distance between them makes instant communication impossible. If they were to reunite, though, that would no longer be the case, so how would time dilation possibly work then? Well, this is where our first version of the twin paradox, the acceleration version, comes in. The 2 observers are Mary and Botan. They both start off on Earth at the same age of 20 years old. Botan stays on Earth while Mary takes off in a ship traveling at 0.6 c. Her destination is a star that's 3 light years away. Upon arriving, she turns around and returns to Earth, again traveling at 0.6 c. Time equals distance over velocity, so it should take 5 years for her to get there and 5 more to come back. If we graph Mary's position over time in Botan's reference frame, you might assume it would look like this. But the thing is, discontinuous changes in velocity like this aren't really possible. In reality, Mary would have to accelerate to turn around. Things are complicated further when you realize she also has to accelerate to get up to speed at the start and to slow down at the end. Thankfully, we can eliminate these last 2 instances by simply having Mary already moving at 0.6 c and only passing by Earth instead of staying. But the acceleration to turn around can't be eliminated like this. If the turnaround takes 1 year, then the total trip will be 11 years. It consists of 3 distinct sections: the outbound trip, the return trip, and the turnaround. Now we'll use the graph to calculate both of their ages. Since this is Botan's reference frame, she ages normally for all 11 years, making her 31 by the point of reunion. But Mary is moving, so she experiences time dilation. If we look at her velocity graph, we can see for 5 of the 11 years, she moves at constant velocity 0.6 c. In that case, the alpha factor is 0.8, which means she ages at 0.8 times the rate, and therefore only ages 4 years during the outbound trip, while Botan ages 5. For another 5 of the years, her velocity is negative 0.6 c, which is just the same thing but the other way. So again, Mary ages 4 years, while Botan ages 5. The turnaround is where things get complicated. Since Mary's velocity isn't constant, it means her alpha factor also isn't constant, so the rate at which she ages is constantly changing. In order to figure out exactly how much she ages, we have to take an integral, but I'll spare you the details and we end up with Mary aging about 0.93 years, while Botan ages 1 year. Combining these, we can see that when they reunite, Botan is 31 and Mary is 28.93. This makes sense so far, but what if we switch over to Mary's reference frame? If the situation is completely symmetrical, then the graph of Botan's position in Mary's reference frame should be exactly the same as before, just in the opposite direction. But the two sides aren't exactly equal. In Mary's reference frame, the star and Earth are both moving at 0.6 c relative to her, which means length contraction applies to not only the objects themselves, but also the distance between them. Using the formula, the distance is now only 2.4 light years, so we have to adjust for that. Also, since the distance is shorter, it now only takes 4 years to clear the distance, so we'll adjust for that as well. This means Mary will turn 24 when she reaches a star, making those two events simultaneous. Since they also happen in the same place, relativity of simultaneity tells us they must be simultaneous in all reference frames. So it makes sense that this is consistent with what Botan's reference frame predicted. The same reasoning also works the other way. In Botan's reference frame, Mary is 24.93 when she passes a star for the second time, so this must be true in Mary's reference frame as well, which saves us from calculating it again. With that, we now have the full graph of Botan's position in Mary's reference frame. Almost. You see, the amount of length contraction Mary observes actually changes as she turns around. At one point, it even reaches 0, in which case the distance from Earth to the star is the full 3 light years. This puts Botan further away at that time, which we have to account for. Now this graph can be pretty confusing to look at, but it makes more sense if we watch the animation in Mary's reference frame. Mary is stationary the whole time, but at time 0, Botan and the star move to the left. At time t equals 4 is the turnaround, during which the length contraction between them briefly goes away, putting Botan even further before it returns as they go back to the right. So the full graph of Botan in Mary's reference frame is slightly different compared to the graph of Mary in Botan's reference frame. But it's still qualitatively the same, where they both see each other leave at 0.6 c, then turn around and come back. So even without doing the calculations, we already know what should happen. Mary is stationary since it's her reference frame, so she ages normally and is 28.93 by the end. But Botan is moving the whole time, and therefore experiences at least some amount of time dilation, which makes her younger than 28.93 by the end. So again, it looks like one reference frame tells us Mary is younger when they reunite, and one reference frame tells us Botan is younger, so we still have a contradiction. But here's the key factor. Postulate number 1 only guarantees the laws of physics are the same in every inertial reference frame. It doesn't guarantee this for non-inertial, aka accelerating reference frames. In the example, the fact that Mary accelerates means her perspective is not an inertial reference frame, so the laws of physics, including things like the time dilation equation, are not guaranteed to hold. Botan never accelerates though, so her perspective is an inertial reference frame, meaning we can apply the equations as much as we want to see that Mary will in fact be younger. In this sense, it's the fact that Mary accelerates but Botan doesn't that breaks the symmetry and resolves the paradox. But there's still an issue. In Mary's own reference frame, she never even moves, and it appears Botan is the one who accelerates to turn around. So why isn't this the correct interpretation? Well, to see why, we can actually apply postulate 1 in reverse. If the laws of physics behave weirdly, then it means you're not in an inertial reference frame. If we look at what Botan experiences during the 11 years, it's just business as usual. where the only way for objects to change their motion is if they're acted upon by a force. The same thing applies to Mary for most of the trip, but the turnaround is different. You're probably familiar with how in a vehicle that's slowing down, objects are flung forward. Well, Mary basically experiences a year-long version of that in her ship. Of course, in our reference frame, we know this to be a fictitious force, where the objects are simply maintaining their constant velocity. But if you attempt to take Mary's ship as an inertial reference frame, then this is just acceleration that comes from nowhere. This is of course inconsistent with the laws of physics in inertial reference frames, which is how we know that this isn't one. And in fact, there are other strange things in this reference frame too, like the fact that Botan appears to be moving faster than light at one point. And this is all because we're in a non-inertial reference frame. Anyway, the fact that Mary's reference frame isn't inertial is how we know her calculations can't predict what actually happens in her reference frame. But that raises the question then, what would Mary observe during the trip? Well, even though her reference frame as a whole isn't inertial, some segments of it are. The only segment where Mary accelerates is the turnaround, so that part is a non-inertial reference frame, but the outbound trip before and the return trip after both take place in separate inertial reference frames. This means we can apply the time dilation equation in each of those, after which we find that Botan only ages 3.2 years on the outbound trip and another 3.2 on the return trip, while Mary ages 4 years each time, totaling 8 years for Mary and 6.4 for Botan. Now we know from Botan's reference frame that at the moment of reunion, Botan is 31 and Mary is 28.93. Since these events are also in the same place, relativity of simultaneity tells us they're also simultaneous in Mary's reference frame, so the ages by the end should be the same as before. That can only mean one possibility. Botan ages the remaining 4.6 years during the turnaround, in which Mary only ages 0.93 years. This means Mary actually observes Botan aging faster than her in a sort of reverse time dilation. And in fact, this can be considered a rule of relativity, where accelerating observers will observe a reverse time dilation in whatever direction they're accelerating, with the effect being greater with further distance. Just like all the effects of relativity, this is something that's been measured and matches experimental evidence. But even still, using the twin paradox to derive a rule, and then using that rule on the twin paradox might feel a bit circular. So here's another way of thinking about it. During the turnaround, the sudden apparent change in the laws of physics can also be thought of as a force that suddenly appears. Mary herself resists it due to the laws of her ship, but everything else, including Botan on Earth and the star, would appear to be accelerating due to the same force, making it uniform through all of space. If we take a page from general relativity, it tells us that fictitious forces in accelerating reference frames like this are actually equivalent to gravitational fields. And general relativity has an additional effect known as gravitational time dilation, where time passes more slowly further into a gravitational field and more quickly further behind. Applying this to the uniform field from before tells us that Botan ages more quickly, which is exactly what we see. Now technically, in general relativity, gravity itself is a fictitious force, which means Botan's reference frame on Earth isn't inertial either. And in fact, the acceleration due to Earth's gravity is about the same as what Mary experiences. However, unlike the uniform field that Mary observes, Earth's gravitational field gets weaker the further you go, as per the inverse square law, so it doesn't actually have a significant effect in this example. So in the end, no matter which reference frame you're in, the result is the same. When they reunite, Botan is 31 and Mary is 28.93. And the key factor that helped us realize that was the acceleration of the turnaround. At this point, you might be sick of the word acceleration, in which case you're in luck because the next version of the paradox is the inertial version, which doesn't involve it at all. But how can Mary return to Earth without accelerating? Well, unfortunately she can't, so in this version it'll have to be her robotic clone, RCM4, that takes her place back on Earth. Specifically, Mary leaves Earth traveling at 0.6 c, with the same destination, a star that's 3 light years away. The moment she arrives, she transfers some data to RCM4, who travels to Earth, again at 0.6 c. Just like before, we can avoid acceleration by having Mary and RCM4 already in motion and simply passing by Earth. But unlike before, we can also avoid the turnaround by having Mary and RCM4 pass the star at the same time, with the data transfer occurring in that exact moment. The data transfer includes an age variable. Basically, however old Mary is at that moment is what RCM4 will set its own age as, with it then increasing as normal with the passage of time. The setup is a bit complicated, but it gives a proxy for Mary's age upon their reunion without actually having her turn around. RCM4's age upon reaching the Earth is simply the amount it aged during the return trip plus the amount Mary aged on the outbound trip plus 20. Since there's no turnaround, it seems like we get a contradiction again. In Botan's reference frame, she ages 5 years on the outbound trip while Mary ages 4, and another 5 on the return trip while RCM4 ages 4, making their ages 30 and 28. But in Mary's reference frame, Botan is moving at 0.6c and only ages 3.2 years on the outbound trip while Mary ages 4. Then on the return trip, RCM4 also sees Botan moving. It's in the opposite direction, but still 0.6c, and therefore, Botan again only ages 3.2 years, while RCM4 ages 4. If we combine these, we get their ages being 26.4 and 28, which is a contradiction. But here's the thing. Even though Mary and RCM4 are in the same place during the data transfer, they still have different velocities, making them different reference frames. Now we know that in Mary's reference frame, Botan is exactly 23.2 at the time the transfer occurs. But these two events happen light years apart, meaning relativity of simultaneity kicks in. And so just because they're simultaneous in Mary's reference frame does not mean they're simultaneous in RCM4's reference frame, despite the fact that the two observers are in the same place at that time. It's not the location of the observers that affects simultaneity, it's the location of the events. It might seem like an issue to have Mary and RCM4 see Botan at different ages when they themselves are in the same place at the same time. But remember, the speed of light is finite, so you don't see things in real time. Instead, you see them as they were when the light was emitted. In the example, the light they received during the transfer will show Botan at age 22. So they will both agree that Botan was 22 when she sent the light they're currently receiving, even though they disagree on when that light was sent out. So what does this mean for the paradox? Well, the calculation that said Botan is 26.4 was based on the assumption that her age at the moment of transfer remains constant after you change reference frames. But now that we know that's not true, the calculation holds no weight. In reality, we can't calculate Botan's age by doing half in one reference frame and half in another. Instead, we have to use the same reference frame the whole time. We already did that once with Botan's own reference frame, but we still have two more to try it on, namely Mary's and RCM4's. We'll start with Mary's reference frame. Botan's velocity is simply 0.6c to the left, since that's how fast she observed Mary to be moving. The same thing applies to the star, and due to this, the distance from the star to Earth is contracted to 2.4 light years. So, at time 0, Mary and Botan both start at position 0, with the star 2.4 light years to the right. But since Botan and the star are moving left, after 4 years it's the star at position 0, with Botan 2.4 light years to the left. It's at this point that the data transfer occurs, and we start tracking RCM4. You might think it would take another 4 years for RCM4 to reach Botan, but that would only be true if velocity is added. Instead, we have to calculate RCM4's velocity using the formula from episode 6. Mary sees Botan move at 0.6c, and Botan sees RCM4 move at 0.6c in the same direction. Therefore, Mary will see RCM4 move at 15/17 of c, which is about 0.88c. This effect basically nerfs RCM4's velocity, meaning it takes a lot longer to catch up. By forming a system of equations, we can see that it'll actually take a full 8.5 years, meaning they finally meet at time t equals 12.5. But it's not the time itself that matters, but instead the ages of Botan and RCM4. Botan maintains a constant speed of 0.6c the whole time, in which case alpha is 0.8. 0.8 times 12.5 is 10, so Botan only ages 10 years and ends up being 30, just like before. Meanwhile, RCM4 is 24 at t equals 4 due to the data transfer, but for the return trip, its velocity is 15/17 of c, in which case the alpha factor is only 8/17. So in those 8.5 years, RCM4 only ages 8.5 times 8/17, which is 4 years, making it 28 by the end, again just like before. So to recap a bit, it seems like we would get a contradiction due to Botan only aging 3.2 years during the outbound trip, but although this is true, when we continue in the same reference frame, the return trip takes much longer due to how velocities combine. This gives enough time for Botan to age the full amount, while RCM4 moves even faster than Botan, and therefore ages much slower, and still only 4 years in that time. And for added context, here's an abridged form to better show the calculations. So, even after switching to Mary's reference frame, we still get the same outcome. The moment they meet, Botan is 30 and RCM4 is 28. But what if we use RCM4's reference frame the whole time? Well, it's actually very similar to before, just in reverse. This time, it's the outbound trip that takes 8.5 years, and the return trip that takes 4. Mary still ages 4 years, followed by RCM4 aging 4 more, totaling 28. Meanwhile, Botan ages 6.8 years on the outbound trip, and 3.2 years on the return trip, still totaling 30. And again, here's the abridged form with calculations. With that, we've confirmed that we get the same result in 3 different reference frames. And if you're curious about the question marks, their values weren't all that relevant to the example, but here's what they equal. If we isolate Botan's column though, we can notice something interesting. In her own reference frame, she's 25 at the time of the transfer, but in Mary's reference frame, she's 23.2 at the time, and in RCM4's, she's 26.8 at that time. And this corresponds perfectly with the predictions from relativity of simultaneity. This raises an interesting question though. Starting with one perspective and then switching halfway through may not be a single inertial reference frame, but what if Mary were to transfer her consciousness or something? What would she actually see? Well, her perspective would have Botan aging 3.2 years, followed by a sudden jump to a reference frame in which Botan's already 26.8, and then finally Botan aging another 3.2 years. But remember, in relativity, we don't see things in real time, so this only refers to Botan's calculated age. What Mary would actually see is Botan very slowly aging 2 years on the outbound trip, followed by her very quickly aging 8 years on the return trip. And this is simply by virtue of when the light from Botan actually reaches Mary/RCM4. Her actual age can only be calculated by retroactively applying the finite speed of light to this data. Anyway, now we're actually going to return to the acceleration version from earlier. You may have wondered what would happen if the time it takes to turn around was made arbitrarily short. Well, now we have the answer. In the limiting case, Mary's perspective would have Botan going from 23.2 to 26.8 in an instant. That makes this hypothetical scenario pretty much equivalent to the inertial version. Instantaneous changes like this might not be possible in real life, but the fact that we get this equivalence shows that we technically didn't need the acceleration in order to formulate and resolve the paradox. It's for this reason that some people declare the twin paradox has absolutely nothing to do with acceleration. In my opinion, this is kind of a debate on semantics. It's not the acceleration per se that resolves the paradox, but the fact that the outbound and return trips are in different reference frames. This sentence is what really reconciled the 2 versions for me and provided a fuller understanding. It doesn't matter if you achieve this change in reference frame through acceleration, through a data transfer, or even through the power of the hypothetical, the result is always going to be the same. With that, we've answered the main question about the paradox. Why is Mary younger upon reunion? Well, it's because our typical rules of relativity only apply for inertial reference frames, which Botan's perspective is and Mary's isn't. But philosophers never stop asking why, and when we do that, it might lead to even more insight about the paradox. So, why is Mary's reference frame not inertial? Well, it's because she accelerates to turn around. But why is Mary the accelerating one and not Botan? This is actually pretty straightforward. If we equip Mary and Botan with accelerometers, then Botan's will never indicate any acceleration other than gravity, which, as I mentioned earlier, has no significant role in this example. Meanwhile, Mary's accelerometer will report nothing for most of the trip, but consistent acceleration for the duration of the turnaround. Now keep in mind, the accelerometers themselves are technically superficial. The important thing is what they demonstrate, which is that only Mary ever experiences acceleration without a source of gravity, which is known as a fictitious force. The only conclusion from this is that Mary accelerates and Botan never does. Both of them agree on this because in relativity, acceleration is absolute. But why does Mary's accelerometer indicate acceleration and not Botan's? The only real answer to this is because we say so. The way we phrase the paradox is that the space twin leaves in their ship and then turns around and comes back. And in real life, here on Earth, we don't just inexplicably accelerate unless we're in an accelerating reference frame, such as a spaceship. Due to this, it's pretty much subconsciously agreed upon that the space twin accelerates and the Earth twin doesn't. But what if we don't subconsciously agree on it? Well, this is how we get the third version of the paradox, the philosophical version. This time, we get rid of the star and Earth and all the numbers. All we know is that you have two observers that start off together, then become separated, and then reunite. You have no idea who accelerates or by how much. This version is by its very nature unresolvable, making it a true paradox. As for the original version, since we subconsciously agreed on who accelerates, there's no contradiction, and the outcome is in a sense already decided. Depending on your definition, this technically makes it only an apparent paradox, not a true one. Now, when people define what the twin paradox is, the conventional presentation is this apparent version, including the Earth, the spaceship, and the subconsciously agreed upon acceleration of the space twin. Despite this, some people insist the only true twin paradox is instead the philosophical version. Some people even go so far as to say the apparent version is pointless to explain because the answer is obvious if you've already agreed on what it is. However, I strongly disagree with it being obvious or pointless to talk about. Instead, I believe everyone deserves a chance to learn relativity, and that intentionally avoiding any non-philosophical discussions of it is counterproductive to making any real progress in scientific education. Anyway, let's get back to the paradox. As I mentioned earlier, the philosophical version is by its very nature unresolvable. In that case, the question becomes not who is the younger twin, but instead why is this unresolvable? Specifically, there are two main philosophical concerns. One, how can we have absolute acceleration but not absolute velocity? And two, how can they both observe each other aging slowly or events in different orders when it seems inherently contradictory? Well, the thing is, from a scientific perspective, it doesn't really matter. The concept of time is simply a useful tool to help us make predictions. The fact that it behaves like this may be counterintuitive, but it doesn't cause any actual contradictions in real life, as we've seen numerous times. But if you're trying to understand the true philosophical meaning of time, then these rules of relativity might clash with your own philosophical interpretation of time. And in that case, if you don't want to just accept that's how the universe is, then there do exist alternative fringe theories that oppose relativity and include things like absolute velocity and simultaneity. The thing is, these theories must make the exact same predictions as relativity, i.e. the ones that have matched decades of experimental evidence. That makes them equivalent to relativity, because there's no experiment that could prove one over the other. When competing theories have the exact same predictive power, scientists just go with the one with fewer assumptions, which is why relativity has stood the test of time and is still the dominant theory over a century later, even if you don't find it philosophically satisfying. My goal with this series is to teach how to understand and apply the theory of special relativity, and throughout this video we've seen how to use calculations to show why the twin paradox doesn't cause any contradictions. For that reason, I now consider it resolved, and I hope I was able to successfully convey how. Anyway, speaking of making predictions, we've done that throughout this video by carefully applying different equations, but the process can sometimes be long-winded and hard to follow. It would be nice if we had a way to switch reference frames without needing to calculate as much. As it turns out, there does exist such a way. It's called the Lorentz transform, and you can use it on position over time graphs to switch from one reference frame to another. If you want to see how we derive the transformation and how it can recontextualize all the established rules of relativity, well, that will be the subject of part 8. For now though, if you learned something new about the twin paradox, make sure to like and subscribe. Thank you for watching, and I'll see you next time. Bye!